Okay, so in this video, we are going to go over the chi-square distribution, the distribution, and the F distribution. Um, so compared to the other concepts we learned about, like the statistical operations and the normal distribution, this video is, I'm trying to make this video a lot more conceptual rather than mathematical, because a lot of the things we're learning here, they're not really going to be applied until later. But nevertheless, they are very important for basic statistical analysis when we utilize data sets. So starting with the chi-square distribution, it's a statistical test that compares data from the observed data to the expected data. So the observed and the expected, those are the key. Those are the key points. And a continuous probability distribution. And again, these type of distributions, they're more useful for inference and testing rather than problem solving, like the statistical operations we did. So for the chi-square distribution, it has two main purposes. It has we're either trying to find the goodness of fit, which means how well the observed data matches the expected data, or the test of independence. So if we have two categorical variables, we want to see if they are independent from each other or not. So whether one of the data sets has any impact on the other. Okay, so let's say that z of I makes up the independent variables given a standard normal distribution. Then the goodness of it can be seen as this formula right here. So the summation of vi squared and up to the m, which I will go over later, just in a couple minutes later. And then this is the independence. We're using two data sets, so it makes sense why we have to use two sigma notations for two variables, in this case r and c. Yeah, but I mean, both these two formulas right here, again, mathematically, even for me, they are kind of challenging on how I can make intuitive sense. So I would try to learn these more conceptually instead of like memorizing these formulas. So if we compare two tables for the independence test, let's say we're trying to compare. Let's say we try to find if the hours of sleep, we'll use the hours of sleep example again. So the hours of sleep, if that's independent from the satisfactory of grades. So for the satisfactory of grades, we either get a response of yes or no. And then for our input variable, we'll say they either slept well, slept decent, or slept poorly. There's no point of inputting arbitrary values here, but the whole point is that these two values, or these two data sets in relation to each other, they're most likely independent, or sorry, not independent. So if we test using the chi-square distribution of these two set of values, then they're most likely to fail. Because we're testing for independence, and from our intuition, these two variables are not independent. But using a similar example, let's say let's say our satisfactory of grade depends on how tall someone is. So like if they're tall, if they're like a medium height, or very small. This test is most likely to pass. Because these two set of variables, they are completely arbitrary to one another. Now, if you want to make technical arguments like, oh, taller people can see the lecture boards better, or blah blah whatnot, that's for different, more specific purposes. But for our case, they're definitely less related than our previous example of sleep and grades. So in general, if the W value is high, for both tests we get a value of W. So if the W is high for either cases, then for the goodness of fit, the expected data does not match the observed data. And for independence, we can say if the W is high, then the two variables we are testing for in relation to each other are not independent. Again, we're not gonna use specific metrics or tests for now. My aim is to just kind of go over these concepts more conceptually. So a lot of this is general, but I think it's still good information to know for down the road. All right, so before I mention about this M right over here, and this M, what it represents is the degrees of freedom. So now I'll explain what the degrees of freedom is. Simply put, it's useful for determining the shape of the chi-square distribution. Again, intuitively, visualizing the shape of the chi-square distribution is a bit difficult, but calculating the degrees of freedom, or the DF, is not very difficult. It's simply put just the sample size. Usually, the sample size minus 1. If we have multiple independent variables or unknown variables, we will subtract n by more than 1. But for now, since we are utilizing a maximum of 2 independent variables or unknown variables, most of the times we'll subtract by 1. And the reason why we're subtracting is that it is a way of imposing a constraint. What that means is when we're utilizing more independent unknown variables that can vary, then we're setting more constraints to our data set. This is kind of hard to explain, so I will give an example. Let's say we have 5 values in a set and the mean has to equal 5. So then we can say X is in a space of any 4 random variables. So let's say we get 7, 8, 2, 5, and then our fifth one, I don't know what this will equal to, but it can vary depending on the previous 4 values. So in this case, we subtract the mu by the number of values in the sample size, which is 5, by 1, because we have one variable that is unknown. All right, so back to the goodness of fit. Again, if we're using this formula right here, just useful characteristics is that the expectation or the mean of W is simply put the degrees of freedom. And then variance is twice the expectation or the degrees of freedom. So as M increases, the chi-square distribution actually, once again, it becomes closer to a normal distribution when the sample size or the degrees of freedom is relatively low. Let's say it's 5, then it will have like a right skew, so like this. Let's try to draw it again. Okay. And then, but when the sample size, again, when it's a sufficient sample size, we'll use 30 in this case, then it will look like a normal distribution. All right, so now for the t-distribution and f-distribution. The t-distribution is a test. We use for a test that we're testing for a single coefficient within a linear regression, and whether the coefficient is significant. So the linear regression is usually finds the coefficient of the x value. If you don't understand what that means, that makes sense because I haven't gone over linear regression yet. But we're basically seeing if like the function made based on the data set, the coefficient, again, it's like another word for slope. So if the slope within the data set that the software try to best fit, if that slope is significant, that the function made by the function of the linear regression made. I apologize if it doesn't make much sense, but that's the best explanation I can do for now. So the F distribution, compared to the T distribution, we are most often than not we're testing for multiple variables. So we're using 2 sample sizes, and we're doing that so that we can test if the variance of the 2 sample sizes is significant. And for the second purpose, we kind of similar to the T distribution, we test if all the coefficients within a linear regression is significant. I'm not sure if this is any or all. I'm guessing this is all because I wrote it that way, but I'm not sure if this is any. I'll have to check later. All right, so these are the t distribution is given by right here. So the z, which is the mu in this case, if it has a standard normal distribution, divided by the square root of w minus divided by m being the degrees of freedom and w being the chi-squared, or the w statistic of the chi-squared. So if we assume a normal distribution or a standard normal distribution, then the expectation of this t statistic right here, it will be given by it will have a mean of 0 and the variance of the degrees of freedom, minus divided by degrees of freedom minus 2. So subtract that first and then divide it from m. And once again, we can interpret this t statistic as if this t value is high, then the coefficient we're testing for is significant, so not close to 0. So if it's high, that means the slope made by the linear regression function is significant. So there is like a noticeable trend within the data set that is made by the linear regression, which the linear regression is always made by the function, made by the computer. It's never done by hand. All right. So if we're comparing a normal to a t distribution, it actually looks very similar. I'll zoom in to draw it a little closer, but if the normal distribution looks like this, then the t distribution looks kind of like this. So this straight line is a normal, and then the dotted line is a t-distribution. Okay, and the reason why they're slightly different is mostly caused by the assumption of the small sample size of the t-distribution. So if the sample size of the t-distribution increases, then it will look like it will go closer to a normal distribution. All right, for the f-distribution calculation, if we are testing for independence, and if both of the variables are assumed to have a chi-square distribution, where the variables are independent from each other, then we can, the k statistic, if we notate it as k, can be given by this formula right here. So the W statistic divided by the degrees of freedom, all divided by the other f statistic divided by the degrees of freedom associated to that variable. And then for the test of the coefficients, it's simply the variance of one of the first statistic divided by the second. And if we always want to divide the bigger, put the bigger variance at the top, so that the k value will always be greater than 1. And then for the visual of the f distribution, it looks kind of like this chi-squared distribution with a low sample size. So kind of skewed to the right. Okay. So in conclusion, without the specific statistical tests, these concepts I taught in this video, they are very general without the specific inferences that we're testing for. But it's still useful to note like the general use of these specific tests, of these different tests I use, because we want to find the relationship between two data sets or set of values, and we're using such characteristics such as the variance, whether they're independent, the goodness of fit, or the coefficients. Okay, and once again, I apologize for kind of the lack of clarity in this video compared to other videos. It is conceptually, this part of the series it's definitely a bit more challenging, but this is the best way I could have explained it for now. All right, in the next video we'll go over more distributions for discrete specifically, so the binomial distribution and the Poisson distribution.